Today, I want to talk to you about a really critical piece of my research, and that is Hilbert space theory. This is nothing new. Hilbert spaces have been studied since the late 1800s in a variety of forms. David Hilbert himself actually started working on Hilbert spaces when he was studying integral equations, and we can talk about that in a later video. He did this work in parallel with Schmidt, and this is where we got our first version of what is called the spectral theorem. The particular theorem I'm going to talk to you about today is what I like to call the fundamental theorem of Hilbert space theory, or more commonly, it is called the Hilbert projection theorem. What is a Hilbert space exactly? Well, Rn is a Hilbert space. It is a complete metric space, and we have this thing that we call a dot product between two vectors, which gives us the norm of the space. Hilbert spaces are made to generalize this idea of dot products and Euclidean space as much as you can in infinite dimensions. In particular, a Hilbert space is a vector space of potentially infinite dimension that comes equipped with an inner product, or a dot product. The inner product has to have the following properties. It's linear in the first variable. It's conjugate symmetric, which means that if I swap the order of the dot product, it comes at the cost of a complex conjugate. The inner product of a vector with itself is positive unless that vector is a zero vector, in which case the inner product of 0 with 0 is 0. Now, with this inner product, we can use the third property to define a norm on vectors in the Hilbert space and also a metric. A Hilbert space is complete with respect to this metric, otherwise we say it is actually an inner product space. Now, immediate from this definition is the parallelogram law, probably the easiest theorem I'll ever present on my channel. Here, let's do the proof in under a minute. This is the parallelogram law. It's basically a thing out of geometry, but I know diddly about geometry, but I am good at Hilbert spaces. And so essentially, if we take the Hilbert space norm, and remember the norm is written this way, so we have norm of x is equal to the square root of x inner product with itself, right? So if you have that, and you put this through here, then you basically get this all together. So you get the sum of x plus y squared plus the difference between x and y squared is equal to twice the norm of x squared plus twice the norm of y squared. So basically, the sum of this squared and sum of this squared is equal to the sum of all of these guys squared. That's parallelogram law. The proof is really simple and just comes down to straight Hilbert space theory. And so all I'm going to do is I'm basically going to expand this guy and this guy in terms of inner products. So since I'm squaring it, we get rid of the square root. And so we end up getting, say, x plus y inner product with x plus y. And if I expand this out, I split it on this guy first, I split it on this guy second, and we're going to end up with a cross term. And so this is basically what we get. We get x inner product with x. We get plus x inner product with y, plus y inner product with x, and then plus y inner product with y. Since this is x plus x inner product with y conjugate, then we add this guy to this guy, and you get twice the real part of this middle piece. So I can go ahead and erase that. And so we get then is we get twice the real part of x inner product with y. And then if I do the same thing with minus signs, we get this. X minus y is equal to, then we get x inner product with x minus twice the real part of x inner product with y plus y inner product with y. This is the norm of y squared, this is the norm of y squared, this is the norm of x squared, this is the norm of x squared. This is x plus y norm squared, this is x minus y norm squared. So we take this guy, and we add it to this guy, then we basically get 1, 2 of these guys, 1, 2 of these guys, and these two guys cancel. And that's the parallelogram law. Boom. I don't know if that was actually under a minute, but I think that went pretty quick. So now let's talk about the projection theorem and see where that takes us. That proof comes from Foland's real analysis textbook, as will the proof of the projection theorem that I'm going to give you in a minute. Okay. So this is a Hilbert projection theorem. It says we're going to let H be a Hilbert space. Duh, that's what we're talking about. We're going to let M be a closed subspace of H, so it's a subset that's also a vector space. Now, for any G inside of H, there's actually an H inside of M that minimizes this distance. I say G minus Q for Q running over M. And so basically, if we take the minimum of all these guys, that is going to be what H a minus g norm is actually going to be equal to. Now, this h is unique, and so that's going to be shown through the parallelogram law, and g can be written in terms of this decomposition, where H comes from M and H perp comes from the perp space of M, or the set of all vectors in H that are perpendicular to everything in M. This is the Hilbert projection theorem, and that's what we're going to be trying to prove. It turns out that the parallelogram law is going to be super important as to getting the existence of this H and also its uniqueness. And that actually will also still work if we change M to being a closed convex set. Now the decomposition, though, it is important that M is a subspace. So yeah, so that's the theorem. Let's go ahead and start proving it. And we're going to start with the parallelogram law, and we're going to get a Cauchy sequence that converges to sort of minimum here. So what we're saying in this theorem is that if we have a closed subspace of H, which is M in this theorem, then we can carve up the Hilbert space as an orthogonal direct sum of M and M perp. This concept is really handy, and we will come back to it again and again and again. One particular place we will discuss it is in the spectral theorem for compact self-adjoint operators, where we will decompose a Hilbert space as an orthogonal direct sum of eigenspaces corresponding to an operator. Now, if you want to see that, I actually have an older video I did. So if you're impatient and you just want to see the spectral theorem for compact operators, self-adjoint compact operators, then you go check out this video here. Otherwise, I'll have it up in, say, I don't know, half a year. In the series. Okay, so how does a proof of this theorem go down? It's going to happen in three parts. First, we need to show that given an arbitrary G in a Hilbert space, that there is indeed an element in M that minimizes the distance to G over all elements in M. The way we do that is to take a sequence of elements of M that tend to this minimum distance, and from that we will leverage the parallelogram law to show that this is actually a Cauchy sequence. All right, so our first goal is to show that H exists and is unique. And so what we're going to do is we're going to start with this minimum over all the Q inside of M. And so we're going to let delta, I should not say minimum because we don't necessarily know it's achieved yet. I should say infimum. But basically, I'm going to let delta be equal to this infimum, and we're going to suppose that we have a sequence Hn inside of this subspace M such that it's going to descend to this delta, or at least converge to this delta. All right, so right now we don't know much about this Hn sequence other than it just takes us to this delta. But what we're going to do is we're going to take this and we're going to see if we can use the parallelogram law in order to show that this is actually a Cauchy sequence. And once we have that as a Cauchy sequence, then what we have is that we know it's going to converge inside its Hilbert space because Hilbert space is complete, and we know it converges inside of M because, well, M is closed. And so then with those two things, it actually gets us the existence. And then for uniqueness, we're going to use a parallelogram again, but in a slightly different way. All right, so let's go ahead and do this one. So we want to show it's a Cauchy sequence, and so we're going to let, say, N and M be natural numbers. And I'm going to just take a look at the difference between Hn and Hm. And so Hn minus Hm. Now, I want to use a parallelogram law, so let's square it. And now we need to figure out what the other pieces are. Well, what I'm going to have is I'm going to take a look at these pieces here. So I'm going to have Hn minus Q, and I have Hm minus Q. So now what I can see is that the difference between these two guys is actually the same as the difference between these two guys, Hn minus Q minus Hm minus Q squared. And so that's actually what this is equal to. Well, then that means if I want to use a parallelogram law, I'm going to have two of these guys norm squared. I'm going to have two of these guys norm squared. And then I'm going to have another term where I add both of them together. And so let's go ahead and do that. Okay, so I have that. Now, what I want is basically what I say is as N and M get arbitrarily large, it's going to be getting down to 0. So what I can actually show is I know that this guy is going down to delta squared. So this goes to delta squared. And this guy goes down to delta squared. And now all I need to do is show that this guy is going to delta squared or something like that. And so what I'm going to do is I'm actually going to factor out this 2. It's going to come out as a 4 over here. And then we can see something pop out of here. It's really useful. I don't necessarily know that this is also going to go to delta. It actually does once we show that it's a Cauchy sequence, but we're not there yet. But one thing I do know is that the very smallest this thing can be is delta. So then what I end up getting is I get this inequality. So I have that this guy is bounded by twice norm of Hn minus Q squared plus twice norm of Hm minus Q squared minus 4 delta squared. And that's because the smallest this could possibly be, the least I could possibly take away from here is delta squared, right? And so that means that if I replace this with delta squared, then this could only make this whole quantity smaller, right? So then that's where we are. And now since this is going to delta squared and this is going to delta squared, overall, this whole thing goes to 0. And well, that means that if n and m are sufficiently large, this can be as small as we like, and thus as a Cauchy sequence. A little hand-wavy with Cauchy sequence, but that's how it goes. Okay, so Cauchy sequences converge in complete metric spaces. So there is an element h in our Hilbert space that this sequence converges to. And since M is closed, that H must also be in M. The uniqueness will also follow directly from the parallelogram law. Now suppose there exists an H and H prime inside of M such that the distance between G and H is equal to the distance between G and H prime is equal to that minimum delta. It is now a proper minimum because we know something satisfies it. So now let's go ahead and take a look. So we're going to use the parallelogram law again, and guess what? We're going to use these two guys. We're going to take their difference. And so we're going to take a look at, say, H minus H prime, and that squared should be equal to twice the norm of G minus H squared, just this piece, plus twice the norm of G minus H prime squared, all right, that's the other piece. We're going to have H plus H prime minus 2G squared. Okay, so we have this. We know what this is, and this is, they're both deltas, just by definition. So it's twice delta squared plus twice delta squared. And now again, we pull out the 2 here. It's really the same proof that we had before. We have H plus H prime over 2 minus G squared. Again, we know that H is a minimizer, H prime is a minimizer. We don't know that the average is a minimizer, but we do know that the very least this could be is delta. So what we know then is that this is less than or equal to, say, 4 delta squared, combining these two, minus 4 delta squared, replacing this with the smallest value you could possibly take. And that is equal to 0, which means that H minus H prime and norm is equal to 0, which means, okay, so we haven't really talked much about the metric space properties of this norm yet, but even if you're not convinced by that, then this basically means that H minus H prime against H minus H prime is equal to 0, which then means that H minus H prime is equal to 0, which means that H is equal to H prime, right? So then there you go. So then H is equal to H prime, and we win. We get uniqueness out of this guy. And so next we're going to talk about part 2. And what part 2 is really going to do is it's going to show that if you take G minus H, that term there actually, and we set that equal to our H perp, whatever you want to call that, that is actually going to be orthogonal to absolutely everything inside of M. And that happens through the use of the quadratic equation and just a touch of calculus 1, which is pretty handy. So you'll notice the only thing we used here about it being a subspace was the fact that the average of two elements in, say, M actually remain in M. But that also happens for closed convex sets. So thus far, the existence of uniqueness theorem actually still applies to closed convex subsets of a Hilbert space. Okay, but what we're going to do next actually requires us to have a subspace. All right, another thing we should mention is that thus far from what we have seen, this really does tell us that this theorem needs Hilbert spaces. It turns out that a norm of a Banach space satisfying a parallelogram law is actually equivalent to the space being a Hilbert space. And in turn, we see that how pivotal parallelogram laws are here already. From here, we have our H, and the decomposition necessitates defining our H perp as actually just G minus H. Now, we don't know that this H perp is actually perpendicular to M yet, but we're going to show that pretty quickly by considering a quadratic function and using some calculus 1 reasoning about zeros and minima, and we're also going to use an idea about vector subspaces, and this leads to demonstrating orthogonality. All right, so for part 2, we have the H perp we defined last time, right? So this is G minus this H, and H minimizes the distance to G inside of M. Then basically what we're going to say is that G is H plus H perp. All right, this is nothing to prove. That is literally just the arithmetic. That's easy. And H perp is actually inside of M perp, which means that it's actually orthogonal to everything that is inside of M. So that's what we want to show. All right, so basically what we're going to do is we're going to start with taking U inside of M, and we're going to show that H perp with inner product with u is equal to 0. And what we're going to do then is we're going to let u just be an arbitrary element of M. And without loss of generality, we're just going to assume that it is inside of R. The reason why we can do this is just basically because if u inner product with H perp is sort of off in this direction over here, then we can just multiply, so this is like theta, then we can just multiply u by e to the I theta, or minus theta, and sort of, or theta, I forget which, and basically we can move it back to the real line. And the reason why this works is just because of the conjugate linearity in the second variable. So I think it needs to be e to the I theta, put it out here, then it comes in as e to the minus I theta in here, and then poof, that's the rotation. So we can just generally assume that it's going to be in R because if u is actually in M, then a constant times u is inside of M as well. And so if the inner product of this or e to the minus I theta was 0, then basically the other one has to be, because it's a unimodular constant, that you can just sort of take out and factor out, right? So we can assume that this guy is inside of R. Now, what we're going to do is we're going to consider this function. So it is h perp minus t times u, and square it. Now this actually turns out to be just a quadratic equation in terms of t, and it takes real values just because this guy is assumed to be real. And you can see it takes real values just because of this. This norm squared is real, this is real, and t is real, so everything's real, right? Now, one thing to note, though, is that if you take a look at this and expand h perp into its definition, then h perp is g minus h. And so this becomes g minus h plus t times u. This is inside of M, which means that this whole quantity is bounded below by delta squared. So the smallest value you could possibly take is delta squared. And when does it take that value? Well, when you plug in 0 for t, h perp is actually just delta squared. You take its norm. So there you go. This is a quadratic function. It takes its minima at 0, and since it's a quadratic function, it takes its minima at 0. That means its derivative at 0 has to be 0. And if we take its derivative, well, then we're going to get 2 times t times u squared, and then we get minus this term here. But then we set t equals 0 because that is where the minima happens. And so then that basically just tells us that this is going to be equal to minus h perp u, and well, h perp u is then equal to 0. So this is orthogonal to every arbitrary u that we can select, and so that means it must be inside of M perp. All right, the last thing to do is really easy, and we need to show the uniqueness of this decomposition, where we will actually show a vector is in both M and M perp. But the only way that can happen is if it's actually just a 0 vector, because it has to be perpendicular to everything in M, but also perpendicular to everything in M perp, and that means it's perpendicular to itself. Okay. So now what we're going to do is we're going to assume that G is actually decomposable as H plus H perp, and for H prime and H prime perp, we're going to have these two decompositions. Now what we're going to show is that H prime has to be equal to H, and H perp has to be equal to H perp prime. This is actually really easy to do. It just starts with this equation. If these two guys are equal, then I can move this guy over, I can move this guy over, and this gives me H minus H prime is equal to H perp plus H perp prime, or minus, H perp prime minus H perp. And then, well, that means this is a linear combination of elements inside of M, so it's inside of M because M is a vector space. This is a linear combination of things in M perp, and so there has to be inside of M perp. The intersection of M with M perp is actually just the 0 vector, and so that tells us that H is equal to H prime, and H perp is equal to H perp prime. And so, because this guy is inside of this, and this guy is inside of this, right? So there you go. So then that is the uniqueness of the decomposition, super easy to show. And that is the Hilbert projection theorem for a closed subspace. If we loosen the subspace to a closed convex set, then we actually keep most of the result with the exception of the decomposition of the Hilbert space. That's because of that averaging we had when we used the parallelogram law. So I want to thank you for watching this video, and I plan on having a full sequence of videos talking about Hilbert space theory, which will lead into operator theory and data science for like dynamical systems and stuff I specialize in. Our next video will talk about the Riesz representation theorem, where we find Maurice Fréchet getting scooped again in the early 1900s. Subscribe and hit the bell if you want to find out more, and otherwise, I hope you have a great day.